So first of all, I'm honored to be a keynote speaker at this workshop. So thank you very much for Tom and the whole ALBA team. Okay, good. So today I would like to talk about the SMOG projects at TU Budapest, which is a set of satellites that we have launched over the last few years. Yeah. So as a beginning, I will start with our history. So our Hungary's very first satellite was Masat-1, which was still a CubeSat satellite with 10 by 10 by 10 centimeter size and a 1 kilogram satellite. It was launched in 2022, and it operated for more than 3 years, and it deorbited as an operational satellite. So that was a very huge step in the history of Hungarian satellites. So the payloads you can see here of this spacecraft, this is a single point of failure tolerant redundant system, and its main payload was a camera on board which took images of our planet Earth. And it was a demonstration that Hungary has the capability to operate a spacecraft, a satellite in space. So as time went on, we still wanted to continue with satellites. But this time, due to lack of time and funding, we decided to go a bit smaller in size. And at that time, when we decided this, PocketQube was a very new standard. So it's 5 by 5 by 5 centimeter, which is, I'm sure everyone knows, is a quite huge challenge for everyone to start working on. So as our department works with high frequency electronics and radar measurements, we decided to have a main payload that represents the work of our department, which is spectrum analysis. So SMOG-1 and SMOG-P are named after Electrosmog. Electrosmog is human-caused electromagnetic pollution that can be measured either here on Earth or rather in space. And that's what we wanted to do. So we chose this as a primary mission for this satellite. The secondary mission of these two twin satellites was a dosimeter, or a total ionizing dose measurement device. And as a third experiment, we put some magnetic materials that had some effects on the satellite, which helped the deorbiting faster. So these are the three main missions of SMOG missions. Of course, both of these satellites are redundant, meaning that they are single point of failure tolerant, and with local intelligence on board. So we have several PCBs inside, which we will see just in a bit. With all of them has their own intelligence. So this is how the system looks like. Redundancy can be obvious, can be seen obviously from this block diagram. Regarding the solar panels, it's a 6-fold redundancy. Regarding all of the other subsystems, except for the battery, they are 2-fold redundant. So if anything goes wrong with any of the subsystems, we can immediately switch over to the other spare subsystem. The exception of the battery is simply because it didn't fit. Two batteries did not fit into this system. So as I said, the MPPTs that were used after the solar panels were 6-fold redundant, and we used 4 by 4 centimeter solar panels on this satellite, which was not produced back then. Fortunately for you, they are already manufactured in this size, But back then, we had to split them into two, which was a quite huge challenge because we did not want them to be damaged. We didn't want the solar panels to be damaged. So the central electrical power system was responsible for protecting all of these other subsystems at the same time as distributing the energy and turning on and off every other subsystem in case of a failure or a deliberate subsystem change. The onboard computer here may look like as if it was just rotated around its z-axis, but really it's the two sides of the PCB. So this is also a redundant machine. It uses a microcontroller. SMOG used an EFM32 microcontroller, and SMOG1 used a PIC microcontroller. And of course, it was responsible for communication between all of the other subsystems, like the UHF radio, the spectrum analyzer, the maximum power point trackers, and so on. So we put on board a redundant antenna deployment subsystem, which was basically a plethora or a lot of capacitors. And these capacitors were able to store energy in case of a battery failure at the beginning of the mission. So we would be able to deploy our antennas even if the battery is completely flat. So we would just charge these capacitors using our solar cells and then use that stored energy to burn the wire that held together the antennas wrapped around the satellite. So regarding the UHF radio, we used two pairs of dipole antennas on this satellite. One was a not matched measurement dipole antenna, which did the primary mission of this satellite, spectrum analysis, from 420 megahertz up to like 800 megahertz, which is the DVB-T band used almost all around the world. Regarding the other part of this subsystem, we used a resonant dipole, a V-shaped dipole rather, because as you might know, a single dipole has a drawback of having a radiation pattern that looks like a donut. And this donut or toroid-shaped radiation pattern has a really deep or a really bad dip at the z-axis, meaning that the received signal of the satellite will be 30-40 dBs lower than compared to the other directions. So a V-shaped dipole can mitigate this. So as you can see on this picture on the right side, the radiation pattern is almost uniform, like an isotropic antenna. The difference between the warmest and the coldest color is roughly 10 decibels, which was confirmed during the operation. So before our mission, we did some proof of concept experiments using a high altitude balloon. So we released a balloon from Budapest. Yeah, I can't really point up there. So we released our balloon from our town, and it went up somewhere around 30 kilometers, and we did these spectrum measurements between 400 and 800 megahertz and plotted them against altitude, which you can see here. So this was the proof of concept that our measurement is viable even in space. So as you can see here, horizontal axis is frequency, vertical axis is altitude, and the color of the plot represents the received signal strength of that altitude and frequency. So at near the ground level, we can see that there are 5 5 distinct channels that are occupied. These are the local transmitter stations around Budapest. And as we go up, the radio horizon opens up, and we can see the neighboring countries' transmitters as well. These transmitters, they use several kilowatts of RF power because they need to cover whole countries or quite large areas. And as we go up higher, we can still see some very strong signals even at 30 kilometers. So if we just multiply it by 10 or 20, this signal level still remains very strong and easily measurable. So that is a proof that we can do this mission in space, and it has some scientific purposes. So just a quick note about ATR-1. ATR-1 is a 2-unit PocketQube, which was the first, Hungary's first commercial satellite. It had some similar functions to the SMOG satellites, and apart from that, it featured 4 different kinds of thermal isolation materials used around the batteries inside the satellite. So we had 4 batteries inside this ATR-1. The 2 satellites, SMOG-P and ATR-1, they were launched from the same pod using Alba Orbital's Alba pod. So thank you guys for this successful mission. And they were launched from New Zealand, Mahia Island, almost exactly 3 years ago. So we just had our anniversary 2 days ago. So before the launch, we had to make some environmental testing. Environmental testing is really a key in the development of even PocketQube satellites. By this, I mean we had to shake the satellite. So vibration tests were carried out from using a sinusoidal sweep from at a 20G force, and also a 65G random peak, which is an effect when the first stage or the stages of the rocket they are dismounted from the rocket. We also did vacuum chamber testing, which is at the same time a bake-out test. We did 3 cycles of this thermal vacuum chamber tests, and all of these tests were successful in terms of all of the 2 or 3 satellites, if we talk about SMOG-1 as well. So the coordination of radio frequencies is something that everyone faces when they build a satellite. So you need to use radio frequencies to communicate with your satellite. Since we intended for all of our satellites to be radio amateur satellites, all of them got a temporary license, and all of them used the radio amateur frequencies of 437 megahertz. So this is the 70 centimeter band. And these were coordinated by national and international organizations like the ones shown here. I'm sure you are familiar with ITU and IRU. NMHH is the National Media Authorization who handles this kind of things. So what is not shown here is the radio amateur call sign of these satellites. So just quickly I will go through. SMOG-1 was HA4C. SMOG-1 was HA5 BME. BME standing for the name of our university in Hungarian. SMOG-P is HA4C, and ATL-1 was HA1 ATL. So we are already at the integration phase here in Glasgow with the AlbaPod, and this went smoothly. Everything fit well, and after the integration, everyone was happy with their satellite. So thanks again for Alba to making our mission a success. Using Electron's, Rocket Lab's Electron rocket, and we went up to space in their mission called Running Out of Fingers, meaning that this was their 10th launch to space. This launch included 6 satellites. 2 of them were our satellites, and fortunately they were deployed successfully, and we were able to make contact with them shortly after the launch. How did we make contact? So if you want to operate your satellite, there are several ways to do that in terms of ground station. We are fortunate enough to have a quite tall building at the University of Budapest, where we were able to deploy a quite large 4.5 meter parabolic reflector antenna, which has a quite large gain of like 21 dB in circular and 24 dB in circular, right-hand circular polarization. On the other end of this antenna, we were able to deploy a hardware radio and also an SDR. So here I would say SDR is the way to go, as it is very flexible and it has a good feedback regarding tracking your satellite. So if you are planning to operate your satellite from home to get the telemetry, I urge you to use an SDR. On the transmit side, we were able to output 1 kilowatts of RF power into this antenna. Fortunately, that is not necessary to control a satellite like this if you have good knowledge of your orbit. So if you have 5 watts of output power, you can even do that, although you might have some packet losses up there. Of course, all of this tracking and remote control is automated, so we do not need to be present at the site ourselves. As the satellite, the ground station is also redundant. So we have a secondary ground station at one of our colleagues' home. It is, as you can see, a different aspect. It has a Yagi antenna, a cross Yagi antenna, also circular polarized antenna. At the middle of this receiver box, you can see the RTL SDR that we are using for reception. The other stuff are for power and output, power amplifiers and other necessary stuff for switching the RF signal. So shortly after the launch, this is what we saw, and this is what you might seek when you are tracking your satellite. So here we can see the different bitrate used on SMOG satellite. So at the bottom side, we see 2.5 kilobits per second. Above that, a bit lower data rate, and then a 5 kilobit per second data rate. The satellite control signal, as you can see, it has a frequency offset, and this frequency offset is, of course, caused by the Doppler effect, which is it lays on the opposite side of the satellite of the satellite's frequency, and this waterfall diagram is already a Doppler corrected signal. So if you are wondering why it doesn't have the Doppler correction, it's because we corrected. Not Doppler correction. It doesn't have the Doppler shift. But at the center, you can see a straight line, which is the DC component of the RTL SDR. That is the Doppler shift, which is corrected. Unfortunately, we have some RF interference, local RF interference in our band, which was not a problem in case of SMOG-P, but in case of ATR1, it caused some packet losses. So ATR1 was very close to SMOG-P's frequency, and we were able to receive them at the same time with an SDR. So one other key aspect to a successful telemetry data collection is the use of a correct coding of your data. So if you look at this image, we see that the uncoded bit error rate curve of a communication and a coded bit error rate curve, meaning that for an uncoded GMSK communication, you need, for a 10 to the minus fifth bit error rate, you need almost 10 dBs of signal-to-noise ratio, which is quite high. In order to achieve that, you need a good antenna, a directional antenna pointed at the correct right direction. But if you are able to use a coding, for example, repeat accumulate and an iterative decoder, you can achieve 10 to the minus fifth only around 2 dBs of signal-to-noise ratio, which is very crucial. Of course, this coding it gives a slower net data rate because it has a coding rate of 1/2. So for every bit of data, you output 2 bits of data. So if you want to receive your satellite, as I said, you have several options. The other option, apart from a large dish, is you can use a handheld Yagi antenna. And this Yagi antenna that you can see here is a very cheap. It's made of measurement tape and a wooden rod, measurement rod, how we call it in Hungarian. And again, as I said, if you use an SDR to plot your received signal, then you can have a constant, not a constant, but an instant feedback of your tracking and of your reception. If you want to do this tracking and Doppler correction of your satellite, you can even use the software that our colleagues written. So this Smog CLI, meaning Smog command line interface program, this is capable of receiving basically any kind of satellite data, which has a telemetry data. So you input your TLE data into this satellite, and then it will track it and output the signals into a file, which you can use, for example, into a WebSDR. The images I showed beforehand were using the OpenWebRX interface or program, which is freely available. All of these are freely available, so I urge you to check them out. And it's a very handy tool for receiving a satellite. So some telemetry data from the mission over time. This is here the battery voltage of our satellite. At the beginning, everything was fine. The battery was full, and we had a positive energy balance, which is also a very crucial point of designing the power scheme of your satellite, is that over time, you should not consume more power than you can produce. So that is what happened at the first month. But after that, something happened. That something we assume was a radiation event, and it caused some short circuits somewhere in our satellite, and then the battery slowly started to discharge up until the point when it restarted. The whole satellite restarted on a dark side of our planet Earth. After this restart, we saw a quite rapid change of a few days, with a few days cycle, where the voltage would go up and down, and at the end it would drop and stay around constantly the nominal voltage of the battery. In the end, we found out that this was caused by the degradation of the solar cells. As I said, the solar cells that we used from Azure Space, they were 4 by 8 centimeter solar panel, which we had to cut ourselves into two, or split rather into two. But for that to be, for us to be able to do that, we had to order them without a protective layer of glass, which would protect us from some of the radiation and the UV that is coming from the sun. So since we didn't have that protective layer, our solar panels degraded faster than we planned to. But despite this fact, the satellite decayed as an operational satellite, which is really good. So it operated for more than 10 months. And during the 10 months, the temperature on board was quite okay. So the main thing is that the battery's temperature should not be below freezing point, which we were able to avoid most of the time. Because if you go under freezing point, then the internal impedance of the battery will go up high, and you will not be able to charge or discharge it properly. Okay, so let's talk about the actual scientific measurements of the satellite. I will stand here because there are some more pictures here. So as a reference, we took the reference measurement over an ocean region where we were sure that there were no transmitter stations in the DVB-T band. And as you can see, the noise level is constant throughout the whole band. But as if we go to the inhabited regions, we can see some spectrum components emerging. This is an example over Europe. This is another example over Europe and Asia. And we did more measurements. Actually, around the whole world, we were able to do measurements. This is an example for North America and Central America. And just to note, the noise floor was around minus 100 dBms, and we can measure signals almost up to minus 60 dBms, which is a huge difference. So if you are into RF, this is 10 to the 4th difference in terms of power, in scalar power. In a comparison, the noise and the measured signal strength over Europe, and really the most important output of this mission was history's first electromagnetic spectrum map of Earth. So here you can see, we could say obviously that over the sea and oceanic regions, we do not have remarkable radio frequency electrosmog, but over the inhabited regions, we have a lot of noise which can mitigate your satellite communication. So if you think about this previous image, this region here is still the 70 centimeter band, which is not very good for satellite communications. So this is something that we need to address, and that's why we need to output more power than like 1 watt of RF power to control the satellite. So yeah, this is the scientific output of our mission. Just a quick word about the decay of the 2 satellites of SMOG-P and ATR-1. Due to the different masses of the satellites, the decay happened a few days apart from each other. I think it was like 1 or 2 weeks apart from each other, and both of those satellites came back as an operational satellite after the mission. In case of SMOG-1, we had a nasty pandemic during the integration time of SMOG-1, so we were not able to transfer the satellite ourselves, but rather we had some help from the Ministry of Foreign Affairs in Hungary, and one of their diplomats took our satellite and brought it to Italy for integration at the middle of the pandemic. It was literally right in the middle of the pandemic where no one was able to travel. The space vehicle this time was a Soyuz 2 rocket, and as you can see, it's not that nice environment in terms of weather. So not the environment is not nice, but the weather. So we were fortunate enough that they launched their satellites or their rockets even in a bad weather, and this was also a successful launch. Although we had some nervous moments because it was a double launch or double deployment. First, this rocket deployed a larger satellite, and this larger satellite, it was not contacted at the beginning, so they were not able to control their satellite, and hence they weren't able to automatically deploy our satellite either. But fortunately, in the end, it was done, and we were happy to receive the first signals of Smog 1. Here you can see several things. So at the bottom half, we see a very narrow signal. This is Morse code, where the call sign, battery temperature, and battery voltage was transmitted. And above that, we see a 5 kilobits per second transmission. And the third thing that we can see is the amplitude change over time of the satellite. And this is due to the tumbling of the satellite. It was tumbling quite fast at the beginning of the mission, but after a few weeks, from like it was tumbling like a few times in 1 second, and after 2 or 3 weeks, it was already tumbling much slower, like 1 or 2 rotations per minute. So you might be familiar with SatNogs, which is a community of satellite trackers. We have a local, so to say, SatNogs team in Hungary, but not just in Hungary, but all over the world. What we can see here is the number of received packets by different stations of satellite trackers. Most of them are Hungarian radio amateurs or enthusiasts, satellite enthusiasts. And you can see that, yes, the number of packets that they received. So as a highlight, I would highlight the first few stations who received over 400,000 packets of our satellite during the almost roughly 1 year. On the fourth position, BME GND is our tracking station. And you can see there's quite large, almost a 30% difference between the first station and our station. And that is simply because of the radio frequency environment. So the first station is located on a mountain hillside, far from any RF interference. And our station is right in the middle of our capital, Budapest. Oh, and yeah, one more thing. Most of the users or most of the tracking stations use their call signs, so we can see where our tracking stations are located. Of course, there are a lot of Hungarian ones, but you can see there are a lot of Japanese ones. Those that start with J character are satellites from Japan. We have some North American stations beginning with an N or a K, and there are a lot of other stations as well. So for the public to demonstrate our measurement or telemetry data, we created a Grafana dashboard where you could track all of the important telemetry data of the satellite. And also there was another website where you were able to see the smog map that we created from our data. Okay, so I would like now to speak about our next mission, our current mission, which will be integrated into Alba Orbital's AlbaPod right about now. So MRC 100, the name itself comes from the name of the radio club of the university, Műegyetemi Radio Club. MRC is the name of this radio club, and it will turn 100 years old in 2024. So that is this name is to honor this anniversary. So this is a 3-unit PocketQube satellite with a maximum mass of 750 grams, and 3-unit, you know the size, it's a bit larger than 5 by 5 by 15 centimeters, and it will also be a fault-tolerant satellite. But one of the new things is that we will host space for different universities from Hungary to launch them to space and do their own experiments. So as you can see, there's a lot of subsystems and experiments on this satellite. Altogether, there are, I think, 17 internal PCBs. All of them do their own thing. So we have the first mission, the primary mission will still be a spectrum analyzer on board. We have two of them, two different kinds of spectrum analyzers. One is an SDR-based, and the other one is a hardware-based spectrum analyzer. And now it can do spectrum analysis from upper shortwave, so from 27 megahertz all the way up to 1.7 gigahertz. And the other one can do analysis from 2.2 gigahertz up to 3 gigahertz. In order to transmit this data and receive this data, we implemented an S-band transceiver on our satellite. And that transceiver at the top is, it has a patch antenna, and this patch antenna, it has a little bit of gain, like 4 dBs, meaning that it doesn't radiate uniformly around the satellite. So we need to have some attitude control of the satellite. The way we do this is a redundant magnetic attitude control, and the determination is also redundant using magnetic, optical, meaning we have an infrared horizon sensor and infrared Earth horizon and sun sensor on board. You can see this in the purple color at the middle of the satellite. And we also have magnetic and kinetic sensors on board. We also have a GPS receiver. If anyone's interested, we can talk about later about the GPS receiver, because it is something that is not very common in this size that can be implemented on a PocketQube satellite. So we have an AIS receiver on board, which is used for vessel tracking over the seas and also rivers. Next to that, we have a dosimeter. It is basically the same dosimeter that we used in the smoke satellites, but my colleague who did this started a startup company, and they now produce a dosimeter, which I will talk about later. We also have an optical sensor on board, meaning we have a camera that can take pictures. And there are the university experiments. I will also talk about them later. So fortunately, we are already at the end phase of the development, and we are at the integration. So we have images of our complete satellite. And this is the actual satellite, the flight model itself, with all its internal panels. And if we wrap it with the solar panels, this is what we'll get in the end. So here you can see the GNSS antenna and the camera and the solar cells on the other sides. We have 4 sides covered with solar panels. They are not deployable solar panels. They are fixed. But on the 4th side, it should cover our power budget. So I will go through each of the subsystems quickly. So this is the EPS1, which is a 4-fold redundant battery charger unit with its own intelligence, of course. Now it fits on one PCB rather than 6 PCBs in case of the SMOG satellites. The EPS2 is responsible for communicating with the limiter switches that we are using on board, which can turn on and off each of the subsystems, and also for producing the 3.3 volt voltage that we are using on board. We have 2 batteries this time. Both of them are isolated with similar kind of isolation materials used in ATR-1 satellite, and this has a lot of sensors, kinetic and magnetic sensors on board. So the onboard computer is again very similar on both sides. The layout actually is it is the mirror copy of its layout on both sides. This time it has a PIC microcontroller which communicates with all of the subsystems. The interesting part is that we are using mainly one-wire UART. So we have simply a ground reference voltage and one wire of simplex UART communication to make sure that we are not using too many pins on the system bus. But for those subsystems that use or that generate a higher amount of data, we use a duplex UART communication. On the right side, bottom left corner, you can see an RTCC timekeeper, so it's a real-time clock and calendar with also a flash memory above, which can store our data in files for later transmission. So if you want to do some scheduled measurements, we can just put them into a flash memory, and later on we can download it from the satellite. Oh, yeah. So the UHF communication transceiver is a redundant system. It uses an XIP module, which is capable of transmitting and receiving LoRa and also GMSK modulations. So we have a quite good range of communication possibilities. And of course, we can change the transmission baud rate as well to suit the actual orbit that is, well, not the orbit, but the apparent orbit from ground. If we have a larger elevation, we can use a large bit rate, and if we have a low elevation, then we can use a lower transmission rate. So the S-band transmitter, it's just a transmitter. It can transmit up to 1 megabit per second of data. And on the right side, you can see the patch antenna that is used by the redundant subsystems, 2 redundant transmitters. The output power in this case is 1 watts of RF out, so 30 dBm out, to which the 4 dB of gain is added of this patch antenna. So the GNSS receiver is an Orion B16 receiver from Skytrack, which provides a useful location data to our satellite. One of the experiments is connected to this, namely that we are transmitting our identification and location data over LoRa modulation, and that is because those of you who have already launched a PocketQubes satellite, you might be familiar with the phenomenon that at the beginning, the NORAD data, the TLE data, is not very accurate. Is there anyone who faced this issue? Okay, good. So we want to address that issue. So we are using this causes, of course, I didn't talk about. So 3 of you raise their hands. You face this problem. You don't know the correct TLE data, and you do not know how much Doppler you have in your transmission, and you lose data at the beginning of the mission. So if we could predict our orbit before the radar data, that would be great in terms of this, because we would not lose as much data as in this basic case. So if we transmit our data using a LoRa transmitter, LoRa is a spread spectrum modulation which is quite robust against Doppler correction or Doppler shift. So you can receive your data using just a single monopole antenna, for example. And if you have knowledge of your timestamp and location, and you collect this data, you can generate and recreate your own TLE data in advance before the radars do this for you. So let's say you have one orbit, you collect several position data, and on the next pass, you can already track your satellite using a larger bit rate. Okay, so for the attitude determination, we use 4 infrared sensors. These are, I think, 42 by 42 pixel infrared cameras or sensors, which can recreate the exact orientation and maybe even the location of the satellite. And this is used for the attitude control feedback loop. The attitude control itself is done by 3 electromagnets. Because of the space, only 2 of these electromagnets are iron cored. And they are custom-made iron cores around which these coils are wrapped. And the third one is a 3D printed, well, sorry, this is not already 3D printed, but machined core. But it is air-cored because of lack of space. So in terms of spectrum analyzers, as I said, we have 2 of them. Well, one turned out to be quite good in terms of space. Actually, we would have been able to compact them into one, but that's something that we decided not to do. So on the right side, we have the hardware spectrum analyzer, hardware radio spectrum analyzer, and on the left side, we basically disassembled an RTL SDR and put the tuner inside this spectrum analyzer, and the data is processed by an RP2040 microcontroller, which is basically a Raspberry Pi Pico's heart inside, but we are not using the Pico itself, but just the microcontroller. So this little guy is, well, on screen it's not very tiny, but in real life it's very tiny. So from the component sizes you can see the scale, but the spacing between 2 pins at the top of this PCB is 2.5 millimeters. So the whole thing is not very, like 2 centimeters altogether maximum, and like 5 millimeters tall. We have the function of this is a limiter switch, meaning that this is the switch that turns on each and every subsystem, and it protects them against overcurrent, overvoltage, and undervoltage. So they do not flat out our battery in case of a short circuit. This is done automatically, so the protection and the switch off is automatic, but the turn on is only done by an uplink command from the ground station. So the AIS receiver, you can see here on the top right corner of the left image. It is basically a hardware radio which is tuned to the AIS frequency of 162 megahertz. And beneath that, we can see the dosimeter of our colleague who created this startup. So I would like to talk about a little bit about this dosimeter. So this is called the rad nano dosimeter, which has a MOSFET inside, which is very sensitive to radiation. So the measurements taken from background radiation can be read out by this sensor, and along with some other telemetry data, and you can transmit this or transfer this data to the onboard computer. For each minute, you have one reading of sensor data. And as you can see, it's very small in size, and it consumes very little power, like below 10 milliwatts. So it's very useful for monitoring your surroundings in terms of radiation. This project is supported by ESA, and it's already a TRL9, so flight-proven readiness level, technological readiness level. I think one or two of this one is already flying in space right now, and this will be the next item, or the next one that will be flown with MRC 100. If anyone's interested, you can contact my friend Gabor at 27g.space. So I will talk shortly about the experiments of the universities. This is also a radiation event detector done by the University of Debrecen. It uses a RAM memory to write in data and read it back later. And if there's any modifications, we can see that there's an event. The University of Győr gave us 2 microcontrollers, which they will monitor the operation of these 2 microcontrollers among each other. The University of Szeged does some temperature measurements and also some quotations and information about the students of their universities. So as we get to the last 2 slides, just before the integration, this image was taken. And as a reference, we should not forget banana for scale. So all in all, before I thank you for your attention, I would like to point out, in my view, what is the 3 most important things to have a successful PocketQube mission. The first one is redundancy. So make sure you have at least some degree of redundancy in your satellite, because you do not have a spare of, for example, your radio and your onboard computer. You will not be able to communicate with it. The second one is testing, and the third one is testing. So the second one, testing, is environmental testing, vibration and thermal, and maybe thermal vacuum testing. And the third one is operational testing. Test your satellite thoroughly. Make sure you test it for several weeks, months in advance, and that will make sure you will have a successful mission, in my view. So thank you very much, and thank you for your attention.